So, good evening everyone joining. So, this is week 4 of CS100 Operating System Fundamentals. This is an NPTEL live session. I am Somnath Hazra. This week we will be discussing some questions about processes and threads. And as you may know that this session is being recorded for feedback to NPTEL. Okay. So let's move to the questions. So the first question is related to cascading termination. We have seen a lot of theory about creation of processes with fork. So so this is related to termination of processes, and in the theory this week sir had taught about zombie processes, orphan processes and stuff like that. So this is about termination. So what is cascading termination? Is it that the orphan child is assigned to the init process? Is it that the parent process waits for the child process to terminate? Is it that the termination of termination of children and grandchildren of a terminated parent process? And is it that the immediate children of a terminated parent process are terminated? So which process is related to cascading termination? So I am waiting for your answers, if anyone would like to contribute. Okay, Nandan says C. Anyone else? Anyone else would like to contribute? Okay, so as you may know that cascading termination is a particular operating system design choice which is related to whether the child process would be terminated or not if the parent process has completed its execution. That is, whether the OS allows orphan children to be executing or not in the system. So it is so that is related to cascading termination. So yeah, okay. So yeah, anyone else would like to contribute to the question? What is cascading termination? So I can see more people joining. So anyone else would like to contribute to the question? What is cascading termination? Okay, let's go to the answer. So it is, yes, you are correct. So it is related to the termination of children and grandchildren if the parent process has already terminated. That is, no orphan processes are allowed to execute in the system. This is an operating system design choice. You may know that in Unix operating systems, an orphan child is assigned to the init process. That is, the init process becomes the parent of an orphan child. But this is another design choice of cascading termination, where if the parent process is terminated, its children, and also if the children had created some other children, that is grandchildren and stuff like that, that is the whole complete tree below the parent process is terminated once the parent process is terminated. Okay. So let's move on to the next question. So this is also related to processes, and we have already studied a lot about processes and fork system calls. So which statement or statements among the following is or are correct? There may be more than one correct. So independent processes require access to shared memory. Cooperating processes can communicate using message passing. The fork system call creates a shared memory for parent and child, and shared memory is controlled by user processes. So would anyone like to contribute? Which of the following statements do you think is or are correct? This is mostly related to shared memory, that you may know is related for IPC, inter-process communication. Okay, then says B and D. Anyone else would like to contribute? Okay, so inter-process communication, as you may know, happens through mainly two mechanisms, that is through shared memory and through message passing. In case of shared memory, the kernel doesn't have that much contribution. It just creates the shared memory, and then it allows the processes to synchronize in between themselves. But in the case of message passing mechanism, we have to the processors have to make system calls in order to pass some message, or in order to utilize the space for the messages that are assigned. Actually, there are no spaces also assigned for message passing mechanism. You have to just pass the messages, and they will be dynamically assigned by the kernel. So yeah. Anyone else would like to contribute? Anyway, let's move on to the answer then. So yes, B and D are correct. That is, cooperating processes can communicate using message passing, and shared memory is controlled by user process. There is no control of the kernel in case of shared memory. The synchronization has to be controlled by the user processes themselves. And if there is some error in the synchronization, it is no fault of the kernel, and it does not the kernel doesn't show it up as a fault. And when you create a child process using the fork system call, it just creates another process. It does not create a shared memory, as we had seen in the previous session also. So what the fork system call does is, it creates a copy of the data, all the data section and the stack section and the heap section, and the code section is not copied though. The code section is just the same, stays the same, and it is just borrowed. But the shared for creating a shared memory, we have to make additional system calls to the kernel, which will allocate a special part of the RAM to be accessed as shared memory. So yeah, that is the part where we have to make the system call for initializing the shared memory, and then after that there is no such contribution of the kernel in case of shared memory. But in case of message passing mechanisms, the kernel participates actively for all the communications among the processes. So yeah, that was the answer. So in case you have joined late, so we were studying about shared memory and message passing mechanisms among processes. So this is the question. So anyway, we will share the questions. So let's move on to the next question. So this is a short numerical, very short numerical. So this is related to the producer and consumer processes. So once when sir was teaching about shared memory and message passing mechanisms, there was a concept of producer and consumer processes. Like, the producer will create a message and the consumer will utilize that message. It does not have to be in case of message passing mechanisms only. It can be in case of shared memory also. For cooperating processes, for example, the producer will create a certain variable or something like that. It will put it in the shared memory, and the consumer will wait for the producer process to be to fill up that shared memory with the required variable, and then it can the consumer process then picks up the variable that is there in the shared memory, and it can utilize it for further access, for further requirements that it can progress. with the with the rest of the process. So anyway, if the producer process is 5 times faster than the consumer process, and the producer fills up a buffer which is of size 100, here like the producer fills up the buffer location with each clock tick, which one is correct? So you can make assumptions, additional things as ideal. So you can make all the additional processes things as ideal to be ideal. You can assume that. So which one of the following statements is correct? That is, the producer has to wait for 10 clock ticks. Wait after 10 clock ticks. That is, the buffer will be filled up after 10 clock ticks, and the like the consumer process has not yet utilized that current location. So and the producer is already ready with the data to be filled up in the current in the location that it has to fill up. So after how many clock ticks will that happen? So will it be after 10 clock ticks, or will the consumer process have to wait after 12 clock ticks, or will the producer process has to wait after 24 clock ticks, or no wait is faced by any process? So anyone would like to contribute? It's a very simple problem. So there are 100 locations, and each location is filled like there are 100 locations in the buffer to be used up by the producer, between the producer and consumer. Okay, ready says C. So yeah, let's see. Anyone else would like to contribute? So there are 100 locations to be used by between the producer and the consumer, and the producer can produce like 5 times faster than the consumer can consume, and there are 100 locations to be used up. So let's move on step by step. Like when the producer reaches the buffer location 100, the consumer is at location 20, right? Because it is 5 times slower. The producer process is 5 times faster, so it has filled up the location 100, and it is at it has utilized only 20 locations, the consumer process. So now the producer can move back to location 1. Suppose we are starting with location 1. So the producer can move on to buffer location 1, and then again it can fill up to 20 locations. Till that time, the consumer process will move another 4 locations, right? Okay. So the buffer will move. So the consumer will move another 4 locations, right? So firstly it was 20 locations, and now an additional 4 locations, after which like the producer has to wait for the consumer to use up that location of the memory. So C is the correct answer. So after 24 clock ticks, the consumer did not utilize the next location, and the producer has to wait for the consumer. Okay, let's move on to the next question. So which among the following do you think requires a system call? Creating a child process, waiting for a process to end, accessing a shared memory, or sending and receiving messages? So which among the following do you think requires a system call? So there may be multiple correct answers also. So as you may know, creating of a child process requires the fork call. Waiting for a process to end, this we have seen for the parent processes. So the parent process needs to wait for a child process or a grandchild to end before it can end itself. So this is often done by the parent processes. Accessing a shared memory. So this is not related to creation of the shared memory. We have already created a shared memory. So now the producer and the consumer are accessing that shared memory, either reading from it or writing into it. So something like that. And sending and receiving messages, this is also related to inter-process communication. So the producer sends some message, and the consumer has to utilize that, reads that message from the memory or something like that. So this is related to the message passing mechanism, which is closely which happens in close contact with the kernel. So which among the following do you think requires a system call? A and B. Okay. Anyone else? So the message passing mechanism, as you may know, it has the disadvantages that it has to be undertaken by the kernel, which is why it is slower, comparatively slower than the shared memory access. But it does not require any synchronization and things like that to read and write among the processes to maintain to read and write the correct data. But shared memory, on the other hand, it does not require it does not require help of the kernel. The processes can do it within them among themselves, synchronize among themselves, and then can access a shared memory, reading and writing. But on the other hand, for accessing a shared memory correctly, they need to have some sort of synchronization mechanism, so that the reading happens only after the writing, right? The consumer process reads something from the shared memory only after the producer has written something into it. Okay. And related to and creating of a child process is done through the fork call. So fork is a system call. So yeah, just the third option is not correct, rest all are correct. So A, B and D. Creating of a child process happens through fork, which is a system call. Okay. So let's move on to the next question. So the values passed to a function, you may know in a C code there are functions. Except for the main function, also there you can create additional functions, additional helper functions according to your requirement. So the values that you pass into the function, where are they stored? In the text area of the process, in the data area of the process, in the stack of the process, or in the process control block that is created for a process in the RAM. So would anyone like to contribute? Stack of the process. Okay. Anyone else? Okay. Data area of the process. Okay. So the text area, as you may know, text area controls the low level assembly language code of the related to your C program, for example. So once you C is a high level language, C, C++, Java, all these languages are high level languages. So once it is compiled, you will get a certain output file, as we were discussing in the previous session. So or a certain executable file depending upon the operating system that you are using. So that executable file actually contains the low level assembly language code that the operating system actually understands. Okay, so that is what is there in the text area. The data area has the global variables and the static variables that are present in the process. Stack of the process contains the local variables. PCB that is just created for the process for storing other informations related to the process, like the process ID, the process like how much clock, how much CPU time it has utilized, which are the open files that has that has been opened by the certain process, and certain things like that, priority of the process and certain things like that. Okay, the stack of the process has the local files, as I said. So the values that are passed on to the function, so they are also the part of the local variables of the of the function of the process. Okay, So they are also stored in the stack of the process. Okay, so option C is correct. Let's move on to the next question then. So next we move to a question related to RPC, which is remote procedure call. So as you may know, so this is a system call to a system which is remotely located, which is not this system, the current system. So there is a client and a server. So you make a system call which is executed in a system which is remotely located through over a network. Okay. So rearrange the RPC activities according to their occurrence timeline. So A is instructions are executed on the server, B is client side stub locates the server, C is parameters are unpacked at the server, and D is parameters are packed at the client. B, D, C and A. Okay. Anyone else would like to contribute? Okay, don't know, no problem. So this is related to remote procedure call. Let's look at a diagram then. So what happens is, what happens is the client system actually does not serve the system call that is to be executed. So it is executed on a server machine on a different system over a network. So the client makes the call. There is a client stub which is like a proxy process which actually identifies the server and the system call that it needs to make to the server. So accordingly all the messages are packed here in the client stub, and then it will be sent through the over a network, and in the meantime the client process will wait for a message to be sent from the server, and on the server side it will receive the client message, and then it will unpack all the messages that are inside and identify the system call and the required parameters, and then it will make the appropriate system call to the server, because the server needs to execute the system call ultimately, and then it will return the messages that are required, and then after returning the appropriate messages following the system call, so those messages also need to be packed, and then those messages will be sent over again a network. So following which the messages will be received and unpacked and then returned to the client. So these all have so there is a network section in between that happens. So which is why we need to pack the messages and we need to unpack the messages. All these processes occur in between. So according to the diagram, we see that the sequence that was given by Nandan is correct. So the client side stub actually locates the server first, and then the parameters are packed at the client, and then the parameters are unpacked at the server, and then the instructions are executed on the server. So the complete process is not explained here, so it is there in the diagram. So after unpacking, it will make the appropriate system call, and then the execution will happen, and the appropriate messages will be returned. Anyway, let's move on to the next question. So this is with respect to the big endian and little endian system. So does both store the LSB least significant bit first, or both stores the most significant bit first? So the big endian system stores the LSB first and the little endian system stores the MSB first, or does the big endian system stores the MSB first and the little endian system stores the LSB first? So which among the four options do you think is correct? Anyone would like to contribute? Okay, I got two answers, D. Anyone else? Okay, it says C. So LSB is equivalent to least significant bit. MSB is the most significant bit. Anyone else would like to contribute? Okay, let's go into a bit of theory. So let's assume that we have a 32-bit integer. So this is the 32-bit integer. Actually, this is the hex code for the 32-bit integer, as you may know. So, so 2 digits actually contribute to a byte, that is 8 bits. So 2 groups of 2 contribute to 8 bits. So so the storage locations are accessed in bytes, right? So so the two characters can be stored in a particular storage location, that means, right? So and in this integer, this is the MSB side, this 0, and this B is the LSB side, right? So in the big endian system, what will happen is, suppose there is a particular memory location A, suppose A is 1000, so 0A, so these two will be stored in the memory location A, and in the next location 0B will be stored, and in the next location 0C will be stored, and in next location 0D will be stored. So in this way, in consecutive locations, the complete integer, the 32-bit integer, can be stored, and the opposite, just the opposite happens in little endian. So since it is little endian, the LSB is stored first. Okay, so 0D is stored in the first location, followed by the others. Okay, so this is what happens, is the difference between big endian and little endian systems. So the correct option is D. Yes. So big endian stores the MSB first and little endian stores the LSB first. Okay. Anyway, let's move on to the next question. So which among the following do you think is or are correct? That is, multi-process creation is heavyweight, multi-thread creation is lightweight, kernels are generally multi-threaded, or all of the above. Which among the following do you think is or are correct? Anyone would like to contribute? Okay. Okay. Anyone else? Okay. This time everybody is saying D. Anyone else would like to contribute? Okay, so for all those who have joined late, so this session, as you may know, is being recorded. So yeah, no problem for joining late, just a heads up. Anyway. So all those who have joined late, so we are discussing a question that this is related to multi-process and multi-thread. So which among the following statements is or are correct? Multi-process creation is heavyweight, multi-thread creation is lightweight, kernels are generally multi-threaded, and all of the above. So which among the following do you think is or are correct? Anyone else would like to contribute? Okay, let's move to the answer. Yes, this is a pretty simple question actually. So for creating a process, you need to for creating multiple processes, as you know, you need to assign the code section, the data section of the memory. You need to create the PCB related to it, and you need to create you need to assign all the spaces, and then you need to bring it onto the RAM, and all these is heavy. So instead of that, multi-thread creation is actually lightweight, where most of the things are being shared. Just the registers and the stack section is not shared. So rest of the things are shared. So in fact, although the multiple threads in between the threads, they cannot write to each other's stack section, but they can access each other's stack section also. So that is what needs to be just created. So it is pretty light. So yeah, multi-process creation is comparatively heavyweight, and multi-thread creation is comparatively lightweight actually. And kernels, they actually they can be single threaded, which solves the synchronization issues and things like that, but it cannot use the CPU effectively. For effective utilization of the CPU, it needs to be multi-threaded, so that it can create multiple threads of a process, and it which can run parallelly, and they can utilize the CPU effectively. Okay. Yeah, so kernels, they of course there is the additional synchronization issue when there are multiple processes running. So that the kernels need to take care of, but that is a good trade-off actually. So just taking care of the synchronization issue, if we can use the CPU more effectively compared to the single process, so that is a good trade-off. So kernels are generally multi-threaded in that case, and therefore all of the above are actually correct. Yeah, let's move on to the next question then. So can you tell me what are some of the benefits of multi-threaded architecture? Is it that responsiveness to allow continued execution? Is it resource sharing is simpler than processes? Is it that it is cheaper compared to process creation and process switching, or is it scalable to multiprocessors? So which among the following do you think are the benefits of multi-threaded architecture? There may be multiple correct options. So which among the following do you think are benefits of multi-threaded architecture? Anyone would like to contribute? A and C. Answers all. Okay. Anyone else would like to contribute? B and D. Okay. So process creation is comparatively heavier on the operating is a comparatively heavier task for the kernel of the operating system, right? Because it as I just said, it needs to allocate separate code section, data section, stack section, heap section. It needs to create everything. It needs to create the PCB and things like that. And similar thing happens for switching also. For switching from one process to another, it needs to bring in the complete process, all the four things that I just said, and the PCB also needs to be brought into the RAM. So it is heavier, right, compared to the threads, where where most of the things are shared except for the registers and the stack among the processes. So creating a so it is cheaper, right? Uh, so the thread creation and switching process compared to the process creation and switching. And of course they are scalable to multiprocessors. It can work in single processor also, so with multiple cores. So yeah, in fact with a single core also there can be multiple threads that can execute in parallel. So of course it is scalable to multiple processors. And resource sharing, of course they are simpler compared to processes, because it does not need to create that many resources, and it does not most of the things are already shared. And related to and responsiveness is actually if there are multiple processes that are there, and one process for some reason it is in the CPU and it has stopped execution, or it is facing an error or something, so it will stop the other processes also for execution in the CPU for CPU time. So what happens is that the other processes will get blocked, right? But if there are multiple threads that are executing, so even if one thread gets blocked because of certain errors or something like that, the other threads can continue execution independently. Okay, so that is what is related to responsiveness. So it is more responsive also. Okay, so yeah, all the things are correct actually. So as I said, the multiple threads share the codes and the data, and like the global data and the static data, and all the open files are also shared. So what is created for multiple threads is that there are multiple copy of the registered data. So since the threads are actually executing independently, there are certain things that that happen independent of each of the processes. So there needs to be multiple copy of the so the register copies need to be independent, otherwise it can create a problem of synchronization. It can not synchronization, it can create a mess, like some other threads data can be overlapped with other threads data. And similar things for the stack. So stacks stores the local variables, right? So so if there is an overlap in between the local variables, also there can be a confusion, right? So that is what happens for the thread. Just the registers and the stacks are independent among the threads. The rest of the things are shared. So yeah, all the things are correct. So let's moving on to the next question. So in this question you need to select the incorrect statement. Okay, the incorrect statement. So concurrency is not possible without parallelism. A parallel system can perform multiple tasks simultaneously. A concurrent system allows multiple tasks to make progress, and a single processor or core cannot support concurrency. So which among the following do you think is or are incorrect? So actually there may be multiple incorrect statements also. So anyone would like to contribute? So this question is related to concurrency, parallelism and things like that. So A and D are incorrect. Okay. Okay. Anyone else? A and D. Anyone else would like to contribute? C. Okay. Says D. Okay. So if you are facing any difficulty with the voice or the screen, please inform on chat. Okay. Anytime if you face any difficulty. Anyway, anyone else would like to contribute to this answer? Okay, let's move on to the answer. Yes, A and D are the incorrect statements. That is, concurrency is actually possible without parallelism. What concurrent execution means is that multiple processes can execute, not on at the same time in the CPU, but it can like multiple processes can be loaded. So in the previous session we saw that there is a ready queue, right? So multiple processes can be loaded onto the ready queue, and there can be process switch, context switch in between the processes. So as we know that the PCB is also called the context of the process. So for contributing to a conversation or something like that, you need the context of the process. So similarly, the operating system for executing a process, it needs the context of the process, and the context is all the details that are related to the context of the process is provided by the PCB, process control block. Okay. So anyway, since there can be multiple processes in the ready queue, and that is actually related to the concurrency. So it may not be that multiple processes execute in parallel in the CPU. So but concurrency is related to the thing that there can be multiple processes in in the ready queue. Okay. So there can be context switch in between them, and multiple processes can execute. Okay. So yeah, a parallel system can perform multiple tasks simultaneously. That is, of course, is correct. A concurrent system allows multiple tasks to make progress. Yes. So as I said, there can be multiple tasks in the ready queue, and all those tasks will actually get to utilize the CPU sometime or the other, and they can make progress with their tasks. And a single processor or core cannot support concurrency. So as I just said, that the concurrent processes can be loaded in a single processor system also. They do not need multiple CPUs or multiple cores for execution. They are just loaded in the ready queue, and one process is actually given the CPU access, and they can continue with the execution. So yeah. So here is an example of concurrent process and a parallel process. So what happens is that, suppose there are two tasks, T1 and T2, and this is a single core system. So what happens is, in task 1 is executing, and in between there is a context switch that occurs. So task 2 is executing after that, and again there is a context switch back to task T1. So suppose there are two tasks in the ready queue, T1 and T2, and so after a certain execution, after a certain units of execution in the CPU, there is again a context switch back to T1, and both the tasks are actually making progress, right? So even if there is a single core or a single processor, but in what happens in if there are multiple cores, and so the multiple tasks that are there in the ready queue, they can make progress parallelly, right? So this is related to the, and even there can be concurrent and parallel execution also. Okay. So that is more complicated. This is quite simple. Okay. So anyway, let's move on to the next question. Okay. So performing same operation on a large performing the same operation on a large data fits which type of parallelism? Data parallelism, task parallelism, or will both work equally well, or will parallelism not work at all? Okay, so this is quite a simple question. So yeah, it is related to data. So yeah, anyone else would like to contribute? So there are large data that is present, and it needs to perform the same operation. Suppose there is an array of 10 numbers and you need to perform addition or subtraction or something like that, as some arithmetic operation on each of the numbers with the same data. Suppose you need to add 10 to each of the numbers in an array. So they can be performed parallelly, right? They are independent. So each A0 can be accessed at the same time A1 can also be accessed. So data parallelism is the right answer here. Okay. So task parallelism actually occurs when there are multiple tasks that are performed on the same data. Suppose there is a certain number, there is a certain matrix or something like that, and you need to perform the transpose, or you need to perform addition, or you need to perform subtraction on the same matrix, and all those things need to be performed. So in those cases task parallelism comes in handy. So where multiple tasks can be performed parallelly. Okay. So data parallelism as okay, let's move on. Next question. So in which kind of buffering queue the sender never has to wait? So this is related to again, these questions are related to IPC. At the end we will again, yeah. Buffering queue, as you may know, is where the sender again there is the concept of producer and consumer. So producer produces certain data, writes certain data onto the queue, and then the consumer can read it from the queue. So in which cases does the sender never has to wait? Where there is zero capacity, like the buffering queue has zero capacity, the buffering queue has bounded capacity, it has unbounded capacity, or none of the above. So anyone else would like to contribute? I have already one answer. So this is also, yeah, comparatively quite trivial. Okay, I got 2 C answers and 1 B. Okay, bounded capacity. Okay, so when the buffering queue has zero capacity, then of course the sender, it needs to wait. For the receiver to be free, and then only it can send a message, right? Because there is zero capacity buffer actually means that there is no buffer. So where will it keep the message or the data that it has produced? So there is no space for that. So it needs to directly send it to the receiver. So in that case, it obviously has to wait where there is zero capacity buffer. In case of bounded capacity buffer, as we saw in one of the previous questions, so ultimately, although it may seem that the receiver is utilizing the data, so although it is of bounded capacity, since the receiver is utilizing the data, the sender may never need to wait. But there can be cases where the receiver utilizes the data slowly compared to the sender packaging the data. So in those cases, ultimately the buffer will run out of space, and the sender ultimately needs to wait at a certain point of time, after a certain point of time, for the buffer to be free, or for the receiver to utilize the already filled up data in the buffer in the queue. Okay. But this is not a problem in case of unbounded capacity. If the buffering queue has unbounded capacity, right, the sender never needs to wait, since the queue has unbounded capacity. So although this is a hypothetical concept, the RAM ultimately it does not have unbounded capacity, right? So ultimately the main memory has some bounds, and obviously a single process will not be given the complete utilization of the RAM also. So anyway, so this is quite a hypothetical concept, but if there is an unbounded capacity buffer, so it will never run out of buffer space. Even if the receiver is utilizing the data slowly, it can directly, it always has some space to send the data, to send the message. So yeah, unbounded capacity is the right answer. Yeah. Okay. Anyway, let's move on to the next question. So in which message passing scheme do we get rendezvous? In non-blocking sender and blocking receiver, on blocking sender blocking receiver, in blocking sender non-blocking receiver, or non-blocking sender non-blocking receiver? So which among the following do you think is the correct option? Obviously there is one correct option. I am not sure how many of you have reached to this part. So it's a very small concept that was introduced. So blocking sending and blocking receiving is a concept related to message passing of IPC, inter-process communication. So in that, so in blocking sending is what happens is this is that as we saw in the previous example, the sender has to wait for the receiver to be free, and then only it can send a message. And in blocking receive, the just the opposite thing happens, that the receiver is blocked until the message is available. Okay, so blocking sender and blocking receiver. Okay. Okay. Anyone else? Non-blocking sender, non-blocking receiver. Okay. So anyway, so the blocking processes are considered as synchronous, because always there will be no out of sync messages that will be stored in that needs to be stored in a buffer or something like that. The sender is producing something and the receiver is utilizing that thing. So it automatically creates a synchronization, something like the sender is meeting the receiver at the same point, right? So does that give an indication? It's like the sender is at the same point as the receiver. There is complete synchronization between the sender and the receiver. So yeah, the answer is both needs to be blocking, then only we get rendezvous. So actually, yeah, so the thing is that, so since as I said, both the sender and the receiver are actually in blocking state, so the sender has to wait for the receiver, and the receiver also, if the receiver is faster, so it has to wait for the sender. Obviously it has to wait for the sender until the message is available. So the receiver can never go beyond the sender speed. Okay, right? Most of the times it has to wait. Okay. So yeah, this is the last question. So a child process may be terminated by the parent in which of these cases? A child has exceeded the allocated resources, the task assigned to the child is no longer required, the parent is exiting, and the OS does not allow an orphan process, or all of the above. Which among the following do you think is correct? Okay, I immediately get one answer. Okay. Anyone else would like to contribute? Okay, I get another answer. I get 3 answers. Anyone else would like to contribute? Okay, anyway, let's move on to the answers. Okay, so yeah, all of the above are actually correct. So once the child has exceeded the allocated resources, it needs to be stopped, and if it requires any restarts, that will be charged by the OS, and accordingly it needs to be restarted with more allocations if required. So, and of course, if the task that is assigned to the child is no longer required, then why does it need to execute? So in that cases also the parent will terminate the process. And in the third case, the parent is exiting, and as we saw in one of the questions, that is cascading termination, the OS does not allow any orphan processes to execute. So in those cases, also the parent needs to terminate the child process. So yeah, may terminate the child process and then exit. So all of the above are correct. So another type of process that may exist is the zombie process. So orphan process is a child process whose parent has finished completed execution. There is another type of process, that is the zombie process, which is actually doing nothing. It has completed execution, but it is still holding the memory. So this is another type of process. Okay. Anyway, so yeah, that was it for today's discussion. Thank you all for joining. Let's hope to meet in the next session after a week. Okay. That is it from my side. Yeah, may have forgot. Could you? Yes, this will be shared actually. This will be online. So yeah, it will be shared through the NPTEL portal, as I am informed. Okay. We regularly keep updating the folders, like the slides that are there in the session, and yeah, those are shared with you, I guess, as we are informed through NPTEL that we need to. Thank you all for joining. So I'll just stop the session now. So rest of you who are online, you may drop off. Yeah.